All right, get ready because we're going deep into pentaquarks.
Pentaquarks, yeah.
You've given us a ton of research on these particles,
I have.
focusing on Maxim Polyakov
Right?
and some anecdotes from Hoon-Chul Kim,
Yes,
a physicist who knew him.
very well.
So we have a mix of theoretical physics and the human side of research.
Yes, very much a mix.
Our mission today is to untangle the history of pentaquark research.
Okay.
We'll explore the theories behind their prediction
Right.
and look at the experimental evidence for and against.
Uh-huh.
But first, I have to ask about this Polyakov.
Yeah.
What was he like as a person?
Well, from what Kim says, he was a force of nature.
Okay.
Kim describes him as really direct and demanding intellectually,
Yeah.
always pushing for clarity and rigor.
Hmm.
Apparently, Hoon-Chul, you're absolutely wrong, was something he said a lot.
Wow. Tough love in the physics lab.
It seems that way.
But it sounds like Kim really valued that feedback.
Oh, yeah,
He sought out Polyakov's opinion because he could connect theory with experiments.
exactly. He was that bridge between the two.
And it seems their relationship went beyond just colleagues.
For sure.
It was like brotherhood.
Yep.
Polyakov even gave Kim a silver cross.
Right, a symbol of brotherhood in Russia.
Which really shows their bond.
It does.
It's so interesting how these personal connections are part of scientific discoveries.
Yeah, it's really fascinating.
Reminds us that there are people with passions behind these breakthroughs.
Absolutely.
And Polyakov was influential beyond just pentaquarks.
Mhm.
He contributed to pions,
Pions, yep.
generalized parton distributions,
Yeah.
even the structure of the proton.
He was prolific.
It shows how interconnected physics research is.
It really does. One person can affect so much.
Makes you wonder how many fields are actually linked.
It does. It really does.
But before we go too far, back to pentaquarks.
All right.
What is a pentaquark?
Well, think of the building blocks of matter.
Like protons and neutrons,
Exact.
which have 3 quarks.
3 quarks. So
A pentaquark has 5.
5, as the name suggests.
They were theoretical for a long time.
Purely mathematical, really.
Until 1997.
1997, things changed.
That's when Dyakonov, Petrov, and Polyakov published their paper
Right.
predicting the up plus pentaquark.
Yeah, the up plus.
But they didn't just predict its existence.
No, they went further,
They predicted a surprisingly narrow width.
meaning it would decay slowly.
Okay, I can sense this narrow width is key.
Oh, it is.
Why was this prediction so surprising?
Well, because pentaquarks are massive.
And massive particles decay quickly.
Usually, yes.
So predicting a massive particle with a narrow width was unexpected.
Very unexpected.
How did their model lead to this?
The chiral quark-soliton model,
The QSM.
it dives deep into the strong force.
The force holding quarks together?
Right.
It describes baryons.
Like protons and neutrons, as a cloud of quarks interacting with pions.
a sort of soup.
So it's not just quarks bouncing around. No, it's more complex,
It's the quarks and pions together
interacting through a field.
that define the baryons' properties.
That's it.
And baryons in this model are solitons,
Yes, solitons
which are stable knots of energy.
in the quark-pion field.
And they get specific quantum numbers through collective quantization.
Right, things like spin and isospin.
So it's like a tiny solar system
Kind of, yeah.
with quarks and pions swirling around.
An intricate dance.
So how did they use this to predict the A+er?
Well, the QSM can predict particle behavior.
Like how they decay.
Exactly.
Okay.
It predicts the axial vector coupling constant for the A+,
And this affects how the plus decays.
into a kaon and a nucleon.
Kaon and nucleon, remind me.
A nucleon is a proton or neutron,
Okay.
and a kaon is another type of meson.
Like a pion.
Similar, yeah.
So these are created when the plus decays.
Right.
Okay, so the model predicts this coupling constant,
Yes,
which affects how the A+ breaks down.
into other particles.
But how does this connect to the narrow width?
It predicts a small coupling constant for the plus.
Small.
Yes, and a small constant means slow decay,
Slow decay.
which
Oh.
means a longer lifetime for the particle.
Which means a narrow width.
Exactly.
It's like a domino effect.
One thing leading to another.
A theoretical model making real-world predictions.
Beautiful, isn't it?
But a good theory needs experimental testing.
Of course.
And that's where things get interesting.
It does get interesting. That's where the experimental side comes in.
Right.
In 2003, the LEPS collaboration,
Okay.
they announced they'd observed a signal
Uh,
consistent with the plus.
So they were trying to create it,
Yeah, they smashed photons into protons and neutrons.
hoping to make a pentaquark.
Exactly.
And they found something.
They did. A signal matching the predicted mass of the plus.
It must have been exciting.
Oh, it was huge.
Like striking gold.
Yeah, after all the
And
theory.
I bet it gets more complicated.
Science rarely has easy answers. What followed was a flurry of activity.
Other groups trying to replicate it,
Yes, exactly. Some, like Diana and Sapphire, confirmed it.
they found the A plus too.
Their signals matched, yeah.
Wow.
Others, like CLAS, had mixed results.
How so?
First they said yes, then no.
So we have some saying yes, some saying no.
It was confusing.
How do they explain that?
Lots of debate.
Hmm.
Some thought the signals were just fluctuations.
Statistical noise.
Yeah, or misinterpretations.
Okay.
Others thought the experiments were different.
Sensitive to different things.
Right, different production mechanisms.
So how they searched for the Act Plus mattered.
It might have, yeah.
Yeah. It's tricky, isn't it?
Particle physics is very subtle.
Especially with particles that are so short-lived
Incredibly short-lived.
and hard to produce.
Exactly.
But you said even the null results had hints.
Well, yeah, sometimes
Ooh.
CLES reanalyzed their data later.
Yeah.
They suggested there might be evidence
For what?
hidden in an interference pattern.
An interference pattern.
Yeah, with the mesonite.
So it's not a clear yes or no,
More like a blurry picture.
with clues hidden in the shadows.
A good analogy.
And this is where the narrow width matters even more,
It does.
because it decays slowly.
Very slowly.
Would that make it hard to find?
It could.
How so?
Many detectors are designed to find fast decays.
Things that break down quickly.
Yeah, with daughter particles that are easy to track.
But the Pass Plus might not do that.
If it decays slowly, no.
So even if it's there, we might miss it.
It might slip through the cracks.
Wow, so the theory affects how we experiment.
It guides our search.
And this led to new proposals
It did.
for finding the path.
For targeted search.
Okay, what kind of proposals?
One idea is to use beams of kaons.
Kaons, okay.
Remember the A plus decays into a kaon and a nucleon?
Right.
So reverse that.
Use kaons to make the out plus buck.
Exactly.
Clever.
There's a group, KLF, who want to do this.
Fire kaons at protons.
Looking for the A plus signature?
Like recreating its decay in reverse.
That's the idea.
Any other proposals?
Yeah, another group wants to use a kaon and a deuteron.
A deuteron.
A proton and neutron bound together.
Okay.
The kaon would interact with the deuteron.
To create the Het plus set.
And two protons.
So two different approaches, both with kaons.
Seems like kaons are key.
They're hoping these will settle the debate.
It's possible.
But even if they find a signal,
Yes.
how do they know it's the Het plus?
That's the challenge, isn't it? It's the big question.
How do you know a signal is a pentaquark?
Especially with something like the A plus.
Yeah.
This is where the real work begins.
Okay.
You have to analyze everything.
Like what?
Does the mass and width match the predictions?
Right.
Does it decay the way it should? And can other experiments verify it?
So multiple lines of evidence.
Exactly.
Not just one sighting.
Right. Extraordinary claims need extraordinary evidence.
And this brings us to another part of Polyakhov's work.
Yep.
The QSM doesn't just predict the app,
No.
it predicts a whole family.
Right. An anti-decuplet
An anti-decuplet.
with the A plus as one member.
That sounds like science fiction.
It's a real term.
What does it mean?
In particle physics, particles are grouped by their properties.
Okay.
A decuplet is a group of 10 particles.
With related quantum numbers.
Yeah, like the baryon decouplet.
Which has protons and neutrons.
And others like the delta and sigma baryons,
So an anti-decuplet is similar.
but with different quantum numbers.
So there could be 9 other pentaquarks out there,
If the GSM is right,
all related to the EP plus.
yeah, that's the prediction.
Wow, that's a bold prediction.
It is.
And it also predicts another pentaquark.
The N1685,
The N1685, what's that?
it's like a neutron,
Also part of this anti-decuplet.
Right.
So finding it would support the whole idea.
including the E plus S. Yeah.
And has anyone seen the N1685?
There have been hints.
Oh.
A few experiments saw a narrow resonance.
There's experiments like,
Grail, Seabell's Taps, A2, and a group at Tohoku University. And what did they see?
a resonance at about 1685 MeV.
Which matches the prediction.
It does.
But we have to be careful, right?
Always.
There could be other explanations.
For the signal.
Like what?
It might not be a new particle.
Okay.
It could be known particles interacting.
In a strange way?
Yeah, we call it coupled channel effects.
So multiple particles mimicking one.
Exactly. Like a case of mistaken identity.
Makes sense.
We need careful analysis and confirmation.
Before claiming a new particle.
Absolutely.
This pentaquark search shows how science works.
How so?
Theory, experiment, analysis, skepticism.
All working together.
It's a process.
It is.
Even if we don't find the EP plus or N1685,
Right.
we've learned a lot.
About the strong force and subatomic particle.
It's the journey, not just the destination.
Well said.
And maybe Polyakov was right.
About the simplest explanation.
Maybe those resonances are pentaquarks,
Maybe.
waiting to be discovered.
Future experiments will tell.
Like the electron-ion collider. That will be a powerful tool.
It seems the pentaquark story isn't over.
Not at all.
It's full of twists and turns.
And the search for knowledge continues.
And it shows how one scientist,
Like Polyakov,
can have a huge impact.
inspiring others to explore.
So, to our listener,
Yes.
keep exploring the research.
Keep learning.
Follow the experiments.
Maybe you'll make the next breakthrough.
The world of pentaquarks is full of questions.
Waiting to be answered.